Hello everyone. Today we will be talking about geometric operations, a comprehensive overview. Welcome to the captivating world of geometric operations. This presentation delves on the fundamental concepts and techniques used to manipulate, analyze, and understand geometric objects across different dimensions. We'll explore how geometric operations are applied in various fields, from computer graphics and game development to architecture and engineering. Join us as we unravel the complexities and beauty of geometric operations, 2D geometric operations, and operations. Points, a fundamental building block in geometry. Points represent a specific location in a 2D space. They are defined by their coordinates x, y on a Cartesian plane. Lines are defined by 2 points representing a straight path extending infinitely in both directions. They can be described by their slope and y-intercept or using vector equations. Circles. Circles are formed by all points equidistant from a central point. They are defined by their center coordinates and radius, enabling calculations of area, circumference, and tangent lines. Polygons are closed figure composed of straight line segments. They can be classified by the number of sides, include special vertices and edges. Next is 3D geometric objects and operations. Cubes are three-dimensional shapes defined by 6 square faces. They are characterized by their side length and have applications in various fields, including architecture and packaging. Spheres are perfectly round shapes defined by their center and radius. They are used in many areas, including astronomy and the design of spherical objects like balls and balloons. Pyramids. Pyramids have a polygonal base and triangular faces that converge at a single point called the apex. They are known for their unique geometry and are found in ancient architecture and modern construction. Cylinders. Cylinders are composed of two circular bases connected by a curved surface. They are used in various fields and manufactured from pipelines. Transformations are translation, rotation, and scaling. Translation involves moving a geometric object to a new position without changing its size and orientation. This is achieved by adding a translation vector to the coordinates of each point in the object. Rotation involves rotating a geometric object around a fixed point called the center of rotation. The angle of rotation determines the amount of rotation, and the direction of rotation can be clockwise or counterclockwise. Scaling. Scaling involves changing the size of a geometric object, a scaling coordinate of each point, making the object larger or smaller according to factors value. Affine transformations. Definition. Affine transformations are a generalization of linear transformations that preserve parallelism but not necessarily angles or distances. They can be represented by matrices that include translation, scaling, rotation, reflection, and shearing. The properties affine transformation preserve straight lines, the ratio of distances between points, and parallelism. They are widely used in computer graphics, image processing, and geometric modeling for manipulating and transforming objects. Applications. Affine transformations play a critical role in computer graphics and image processing, enabling tasks such as object manipulation, image warping, and perspective projection. They are also used in robotics, computer vision, and other fields. Projections and perspectives. Orthographic projection. This projection method projects objects onto a plane perpendicular to the direction of view. It maintains parallelism, lines, and preserves relative sizes but lacks depth information. Perspective projection. This method creates a more realistic representation by projecting objects onto a plane as if viewed from a specific point. Parallel lines converge and objects appear smaller further away, providing depth perception. Applications. Orthogonal projections are often used in technical drawings and engineering designs. Perspective projections are widely used in computer graphics and animation and video games for creating realistic image dynamics. Intersection and intersection detection. Line-line intersection, line-plane intersection, sphere-sphere intersection, and applications. The line-line intersection involves finding the point where two lines intersect. It is solved by finding the point where the equations of the lines have the same solution. In line-plane intersection, it involves finding the point where a line intersects a plane. It can be solved by substituting the parametric equations of the line into the equation of the plane. Sphere-sphere intersection. Determining two spheres intersect involves comparing the distance between their sectors to the sum of their radius. If the distance is less than or equal to the sum, they interact. Applications. Intersections detection plays a crucial role in comparison, collision detection, ray tracing, and other applications determining whether objects collide or overlap. Next is bounding volumes and spatial partitioning. Bounding volumes is simple geometric shapes that enclose an object used to efficiently approximate its extent. Examples include bounding boxes, spheres, and capsules. Spatial partitioning, dividing a 3D space into smaller regions, enabling faster object location and intersection detection. Methods include OC trees, KD trees, and BSP trees. Bounding volumes can be used for collision detection, ray tracing, and object visibility testing. Spatial partitioning improves the performance of collision detection and other applications that involve searching into large spaces. Optimization techniques for geometric operations. Uh, Spatial data structures using data structures like OC trees, KD trees, and BSP trees to efficiently store and search geometric operations. Hierarchical representation, representing complex objects using hierarchical structure, enabling faster processing and manipulation. Approximation techniques, approximating geometric objects using simpler shapes to reduce computational complexity. GPU acceleration, leveraging the parenting power of GPUs for operations and remembering. These are the logical decision, defeat actions in a loop, and do sequence of action. Applications and case studies. Geometric operations are at the heart of many modern technologies and applications, enabling the creation and manipulation of virtual worlds, realistic simulations, and innovative designs. Here are some notable applications and case studies that demonstrate the power of geometric operations. Computer graphics and animation, video game development, virtual reality and augmented reality, architecture and engineering, medical imaging, and computer aided surgery. So these were the application and the case studies that could be studied in order to understand geometric operations. I hope you liked this video about computer graphics and geometric operations. Please like and share this video as much as possible. Thank you.